of minivans being coded, for the companies that are actually going to be paid to fix the technical debt because it's in their interest. It's like coding me a new minivan, but how do you present this argument that you're making here to the CFO that ought to be smart enough to look beyond what's the cost per hour for an Indian programmer?
Let me respond by way of the slide after the coming slide. I will go back to the previous slide in a minute. But to Michael's question about demonstrating those trade-offs of higher level of technical debt that I will need to pay off down the line versus better quality code for which I might need to pay now, the way I would suggest to do it is by equating value, cost, and technical debt. And let me exemplify it by way of the graph that you see here. This thing is time. This one is the level of dollars, whether net present value, cost, or technical debt, which are the three elements that we talked about in the agile triangle. Now, the various readings that you see here are taken from a time machine, namely, not literally in this case because I constructed it by hand, but like we have shown the results on Cassandra from the Cassandra figures before, this is the way you would do it. Now, what is happening here? You have a project that starts accumulating cost because the guys are doing whatever they are doing, some application. And this is, at the beginning, completely linear. I worked 1 week, I worked a whole iteration, I worked 2 iterations, etc., etc. Now, at this point in time here, we ran technical debt analysis. And guess what? We found out that we are really getting deeper in debt than building equity. Namely, the amount of technical debt here could be something like $1 million, while we only built an equity of $500,000 in terms of the cost that we put into the project. Now, what happens typically during this period, this triangle that you see here, we really stop doing new functions and features and get very strong on reducing the technical debt. In a way, all the cost that we put in here is going towards reducing the technical debt. At a certain point in time, we reach the point where the two curves intersect. Namely, the technical debt is not any more higher than the cost. Now, what happened during this period that we were working on the technical debt? Obviously, we will be coming later to market than we expected, or we would be delivering less features than we were planning. In either case, the net present value went down because either you lose some on the cash flow because you come later to market, or your release is less attractive to the customer because of lack of functionality. Now, as you continue to push back on the technical debt and reach the point that it's insignificant, then you have an interesting phenomenon. Your velocity in terms of developing after you pushed back on the technical debt actually increases beyond the level that you had at the beginning. So the velocity is not just the velocity that we count in Agile in terms of team velocity. It's also a function of the quality of the code, the amount of technical debt that you have. And the very same team, if you have them work on poor quality code versus reasonable quality code, will have different velocities. So what happens is that all this hard work here, even though it might have looked as a delay at this phase, actually increased your velocity, and here your productivity is at the level that you produce more and more function and features, and very possibly you have the net present value exceed the original level that you expected. If you take a look at your own charts, Michael, about the number of bugs that, about, what's the name of his company? Quick Solutions? The number of bugs that were in the Quick Solution chart, they really demonstrated beautifully, namely an unusual low level of bugs, which enabled them to run quickly and deliver probably better than on time and with very high productivity.
And Israel, one thing that's interesting of the 3 case studies, BMC, Follett, and Quick Solutions, the defect rates in descending order were all related inversely to time pressure. So by relaxing time pressure, you could reduce the order of magnitude, the technical debt, by say an order of magnitude. So it's fascinating to me that that there's interdependency here. High time pressure, throw a lot of people on the project, create more bugs, especially in a waterfall project. BMC did not see that to the degree that a waterfall project does. Follett had a slightly relaxed schedule compared to BMC's high time pressure. They had 50% fewer defects. Quick took an even more bold approach by really not getting crazy about the deadline, and they were at the 90th percentile in terms of low defect rates. So the technical debt was extremely low there, just by allowing a little bit more time and using a small team.
I could not agree more. As a matter of fact, my consistent recommendation to my clients is don't try to push the dimension of productivity or the dimension of time to market. Push on the quality, and those 2 other dimensions will follow. If I take a look at the slides that you presented earlier today with the relative number of bugs and other attributes of the projects, to me they are simply a different representation of the considerations that are explained here. So for the CFO, we go back to the core question. For the CFO, we go back to the fact that everything can be expressed in dollars. And if you come to your CFO and show him that the technical debt, for example, is higher than the value that is expected to be derived, I would think the person would get the message and would have the mental model to work with. Let me mention one other thing that is very related to what you speak about, Michael, and this is about early warning signs. If you have a technical debt of $10,000 or $100,000 or whatever the figure might be, to itself is not meaningful because this is a figure which is out of the project context. However, you can do quite a few interesting things. First, if you look at technical debt per line of code, I should have struck out the K there, then if you have it above, I would say, $1 per line of code, this is not a good sign. Now, where precisely you draw the line, at $0.5 per line of code or $1.3 per line of code, etc., this will differ from one company or another. But I would say if you have a code base and your technical debt on it is significantly higher than $1 per line of code, you can expect problems. So you have a way, while you go along on developing your projects, to use this as a proxy for risk. If you accept for a minute the assumption that when it's above $1 per line of code, one could expect problems, then here you have a quantifiable number that you can plug into your risk models. Another one, you can take a look at technical debt as percent of the cost. And here there is something that is a little tricky. You need to look at declining technical debt as percent of cost. Because if you take a look here, for example, here the project stabilized on a certain level of technical debt, and the technical debt as percent of the cost is going down because the cost is going up, technical debt is being kept constant. So you can't just say, I will look at technical debt as percent of cost, because this would create a situation of this technical debt line growing in parallel or in parallel with the cost line. you need to look at the way it declines as function of cost, because obviously you work another week and another month and another year and so on and so forth on the product, and your cost goes up. So in a healthy project, you would expect the ratio, namely of technical debt to cost, to go down. Another example is going back to what we talked about before, about one component of the technical debt, the cyclomatic complexity. This is a study that is taken from, I don't quite know how to pronounce it, Energy. And what they did, they looked at 12 projects, I believe, and looked at cyclomatic complexity per class. They actually looked at cyclomatic complexity per file, but as this was Java language, I will allow myself to say, assume that the file and the class are pretty similar. So what you have here is a cyclomatic complexity from 0 to 1. And again, this is per class. And the error proneness of the various modules on the other axis. What you see here, when cyclomatic complexity per class reaches 74, you are practically guaranteed that you would have a problematic module on your hands. So what happens in terms of various warning signs, this is a good way to get a handle on the prospect of a module in your set of modules being problematic in the future. And mind you, you are getting the warning early during development. It's not that you are starting to realize 1 year after you released it that you have a problem with a certain module. You get the early warning sign here by way of analyzing the code. If you take a look at this point here, then I think this is 38, is that correct? I have difficulty reading from here. Is it 38 here?
Yes.
So at a level of cyclomatic complexity of 38, you have a probability of 50% that the module on which you checked it, or the class which you checked, would be problematic. And the power of this technique is that instead of coping with a mountain of technical debt, you are able to pick the bad apples. Namely, hopefully, most of your classes are under 20 in terms of cyclomatic complexity. You are able then, let's say, to put the cutoff point here at 38 and say, we shall start working on all classes which have got a higher cyclomatic complexity than 38. And if you want to be more strict, you of course can set it any place you would like here. Last but not least, you can look at combinations of factors which are part of technical debt. And this is demonstrated in this two-dimensional heat map here. The heat map is arranged by size. The heat map is arranged by size and is arranged by color. Size is indicative of complexity. So project P1 that you have here is obviously the most complex project in this set of projects. Color, however, indicates the overall quality. And for example, P2 being larger than P5 obviously has a higher complexity than P5. However, P2 has been coded to pretty reasonable quality, while P5 has very poor quality. So in terms of your technical debt reduction strategy, you would obviously go after P5 and very probably go after P1 as the next one that needs to be addressed. Let me move on now to end-to-end governance, and I will need to rush it up a little bit as our time is about to be exhausted. Take a look at this process control view of software development, or Scrum if you please. Basically, what is a Scrum process? You have inputs in terms of requirements. you have the process and output in the